Alright, got the final here for Jordan Fugelstad. It's me, just to verify, just in case. I don't know if people are stupid and try to do something else. Alright, so first number one. Add curved arrows to show the first resonance structures can be converted into the second and reverse. The thing with resonance structures, atoms stay, electrons move. That's what the arrows are showing. So out of the CH2 there, going into the bond, out of the pi bond, coming out. And it can be either way here. So we're going back out of the double bond into the CH2, out from the outside into forming the pi bond again there. That one's pretty easy and straightforward. Number two, draw the products of the proton transfer reaction. Label the acid and base in the starting materials and the conjugate acid and base in the product. Show the arrow formalism. So like I said, the arrow formalism is showing the electrons moving there from the CH3O to the H, out of the bond to the O. This is the acid over here. This is the one that's going to donate the proton. That would be the base, the one that accepts the proton. In doing so, going back and forth either direction here, that's what the arrow shows there. So forming the conjugate base, that's formed when the acid loses the proton. And then the conjugate acid here, which is formed when that base is accepting the proton. And like I said, this is the Bronsted-Lowry. Big thing to remember is the proton transfer compared to the electron transfer, which is the other reactions we learned. All right, numero 3. Circle and name the functional groups in each molecule. This is for penicillin, kind of an important antibiotic. So we have the aromatic ring. Things to remember with these, like with the functional groups, is just remember the bonds. So like for the aromatic ring, it's a phenol identity. The two amides here, kind of important to point here and here. You gotta remember it's a CONH bond there. And then with the sulfide here, it is a SR bond. And then the carboxylic acid is, COOH bond. And that's how you distinguish those there with that. Page 2. Not page 3, page 2. Alright, so, really long name, don't want to try to butcher that. Is a marine natural product with interesting biological activity. Indicate the chiral centers with the asterisks there. The big thing to remember with these centers is that it's basically a carbon atom bonded to 4 different groups. Well, not basically, that's what it is. The big word in there is different. That's what distinguishes it and actually makes it a center there. So with this one, distinguish 1, 2, 3, 4, 5, and 6. So there are 6 on there, and those are all connected to 4 different groups. Like I said, that is the big difference here. With those, yeah, it's kind of tricky because sometimes if there's 2 of the same connected, it's basically, I would say, mostly never actually a center then. At least from what I've seen in the class so far. There could be outstanding circumstances, of course. Alright, number 5. Draw the most stable conformer of cis-1,3-cyclohexane-Dale. Alright, so with this, the big thing to remember is, there's the actual answer there. The big thing to look at here is axial versus equitational. Sorry, my English sucks. So with axial, they are above and below, whereas with equatorial, they are like on a plane. It's pretty self-explanatory with the words themselves. Axial on the axis, equatorial on the equator, basically, is how you look at it. And using that, you can use the equatorial to form the most stable version of the conformer. Kind of hurrying through these ones just because these last couple take a little more to explain here. Alright, so number 6. Draw the stepwise elimination mechanism using the arrow formalism of bond breaking and bond making to predict the major product here. So, things to remember with this is we're looking at an E2 mechanism. With that, you have the leaving group comes off creating a carbocation. But with the base, is not really used to pointing on this. So with this, you have a strong base over here, and then you have a proton. So the base plus the proton forms the bicarbon, and then over here, switch hands here. Yeah, there we go. Right here, we will have the pi bond forming right there. And then, like with the arrow formalism, that's showing the electron movement there, going from the wedge formation inside there, and that is what is forming that pi bond. All right, where did I put number 7? Number 7. Draw a stepwise mechanism showing the arrow formalism and show the product of this unimolecular substitution if the nucleophile solvent is methanol, which methanol will be right there in this situation. Okay, so with this, it's important to remember that the Cl right there is the leaving group. And then you can see from the arrow formalism here, the electrons coming out into the Cl. Like I said, methanol is the Nu there. The loss of the Cl creates a trigonal planar, and then the another thing to remember is the Nu, this guy, the methanol, can attack from either side. So we have this side here, this side here. So it can attack from either side there, and then with using the Bronsted-Lowry acid-base reaction, it leads to a neutral organic product, which is readily losing protons. So that's what we end up with over yonder here. And it's a two-step S1 mechanism. So basically using substitution there. So number 8. Draw an enantiomer of the given compound. A thing to remember with these is they are stereoisomers, mirror images, and they're not superimposable. So the easiest way to remember these I found is, or how to do these, is using, I think it was in the book, not the lecture, but there's an example of using your left and right hand. I mean, it's the same hand, but you get the idea. They are mirror images of each other, but they are not superimposable. Superimposable would be the example of the socks. Socks are mirror images, and they are superimposable. With this, we do not want this to be superimposable. We just want them to be stereoisomers, and we want them to be mirror images of each other. So how we come up with, so don't mind my little mark here. I don't know if I was right, BR twice or what I was doing. All right, B. What is the UPAC name for the structure below? So with that, I'll distinguish that is an S. So first we have S. So with the S, actually, first, I'll go with the chloro. That's the easiest thing to explain there. So with the chloro, it comes off the carbon 3, and we're counting from left to right and using the C before E rule. So that's how we come up with the 3 chloro there. And then with the 6, the ethyl comes off of the carbon 6. Again, we're going left to right. That's kind of the important part there. And then the octane will come from that 8 is the longest carbon chain there. 1, 2, 3, 4, 5, 6, 7, 8. Wow, cannot read an 8. All right, so that's an 8 there, and that's where they come from with that. The S comes, back to the beginning. The S comes from using the counterclockwise when drawing it out there. So with that, you get S3, chloro, 6, ethyl, octane. And you have the name for said structure. That's all I got for you. let me know if, I don't know, if you need them further explained or whatnot. I think I got the gist of what you were asking, wanting us to, how in depth you want us to go with this, but just let me know.